Welcome to the Padhai Kar Lo JEE preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is the polar representation of complex numbers, and why this alternate form makes certain operations dramatically simpler. Let's begin. Every complex number z equals x plus iy can genuinely be rewritten in polar form as z equals r times cos theta plus I sin theta, where r is the modulus, the distance from the origin equal to the square root of x squared plus y squared, and theta is the argument, the angle, from the positive real axis. To convert from Cartesian to polar, compute r directly using the modulus formula, then find theta using the actual signs or x and y to correctly determine the quadrant, combined with tan theta equals y over x. To convert from polar to Cartesian, simply compute x equals r cos theta and y equals r sin theta directly. This conversion is genuinely straightforward in this specific direction since it just requires substituting theta and r into these two formulas. Polar form is genuinely often written even more compactly using Euler's formula, e to the power I theta equals cos theta plus I sin theta, giving z equals r e to the power I theta. This exponential notation makes multiplication and division genuinely trivial, since multiplying complex numbers in this form just multiplies the moduli and adds the exponent, exactly matching the familiar laws of exponents. This exponential structure leads directly to JEE Moivre's theorem. For any integer n z to the power n equals r to the power n times cos of n theta plus I sin of n theta. This genuinely powerful result lets you raise a complex number to any power without ever needing to multiply it out repeatedly in Cartesian form, dramatically simplifying calculations that would otherwise require expanding binomial-like products many times over. The Moivre theorem also genuinely provides the standard method for finding the nth roots of a complex number. The n distinct enter roots of r cos theta plus I sin theta are given by r to the power 1 over n times cos of theta plus 2k pi over n plus I sin of theta plus 2k pi over n, where k takes every integer value from 0 up to n minus 1, generating exactly n genuinely distinct roots, evenly spaced around a circle or radius r to the power 1 over n. A frequently tested trap involves genuinely remembering to use the principal argument restricted specifically to the range negative pi to positive pi, when initially converting to polar form. Using an incorrect or inconsistent argument value will genuinely propagate errors directly through every subsequent power or root calculation. Also remember that polar form is genuinely most useful specifically for multiplication, division, powers, and roots, for simple addition or subtraction of complex numbers. Converting back to genuine Cartesian form first is almost always considerably easier. Let's recap. The polar form of a complex number z equals r cos theta plus I sin theta, or equivalently r e to the power I theta, makes multiplication and division trivial by multiplying moduli and adding arguments. The Moivre theorem, z to the power n equals r to the power n times cos n theta plus I sin n theta, extends this to powers and gives a direct formula for the n distinct enter roots, evenly spaced on a circle. Always using the correct, consistent principal argument and choosing polar form for multiplicative operations while sticking with Cartesian form for addition are the keys to avoiding errors. That's the polar representation of complex numbers. Keep the Moivre theorem and the enter roots formula sharp. They turn intimidating power and root problems into a mechanical process. If this video helped, please like it and subscribe to Padhai Kar Lo for more JEE preparation content just like this. See you in the next one.